Hello and welcome to another lesson on A-level physics. Today's learning intention is to understand the electron diffraction experiment. You'll remember we mentioned that at the end of the last video about the Rutherford alpha particle scattering experiment. The success criteria for today is to know how nuclear radius was determined using the electron diffraction experiment and to be able to calculate a quantity known as nuclear density. So, let's begin by recapping something that we will have done in year 12. Most of this is from the waves topic, but you might have done a little bit of this in quantum physics as well. So first of all, I would like to sketch what would be seen if monochromatic light were shone at a diffraction grating. Sketch what would be seen by electrons if electrons were diffracted by a crystal structure, a 3D crystal structure at that. And then I wanted to explain why the pattern is not the same. Now please don't get too hung up on the fact I'm asking you for sketches. I don't need them to be to scale or anything like that. Just roughly what patterns would be seen from the two different situations. Pause the video, have a go, and then press play. So, when we shine monochromatic light at a diffraction grating, we will get a pattern similar to the one shown there on the board, i.e. we would have a series of fringes, bright fringes and dark spots, and we would find that the one in the centre is the brightest and they will get dimmer as we go further and further away. Now, by contrast to that, when electrons are diffracted by a three-dimensional crystal structure or lattice, what we would find is that it produces diffraction rings, which is what I've shown there, where we have a bright centre and then concentric circles of dark and light. Now, why is it that one of them actually produces what you could call almost like a one-dimensional pattern in a sense, and the other one is producing a two-dimensional circle? Well, the reason for that is all to do with what is causing the diffraction to take place. In a diffraction grating, all of the grating spacings are in one plane, i.e. they're either all vertical or all horizontal, etc. However, in a crystal sample, the spacings are not all in the same plane, which is why we get diffraction rings produced. So now let's have a look at the diffraction of electrons then. What we've got here is a setup shown on the board where monoenergetic, high energy electrons are being fired at a target. The setup is of course very similar to that Rutherford used, but the key difference here being that we're using electrons instead of alpha particles. That detector is of course able to be moved around the semicircle shown by the dotted line. When a beam of high-energy electrons are directed at a thin, solid sample of an element, the electrons will get diffracted by the nuclei. The diffraction happens because the de Broglie wavelength of such high-energy electrons is of the order 10 to the minus 15 meters, which is approximately the same as the diameter of the nucleus. The detector used to measure the number of electrons per second is moved through different angles as shown, and the number of electrons measured per second in different angles is recorded. Now that data can then be used to produce a graph like the one I've shown you there. So you can see when the diffraction angle is 0, we get the maxima of electrons, we get the most electrons per second. Now you might well wonder why is it that the electron graph, it looks like that, because you can see that as the diffraction angle gets bigger, the number of electrons detected per second decreases to a minimum, but then it rises back up briefly before falling again. Why does it have that pattern? The reason is that there are two phenomena going on here, not just diffraction. The electrons are both diffracted and scattered. Now, the cause of those two effects are different, but they both result in the electrons changing direction. The shape of the graph is a result of the combination of both of those effects. Electrons are scattered because of their charge. We know that electrons have a negative charge, but obviously the nuclei have a positive charge. Similar to the alpha scattering experiment in the sense then, but of course the electrons will be attracted to the nucleus instead of being repelled by it. The effect of that causes the number of electrons to be detected per second to reduce as the angle of the detector is increased. The diffraction of electrons causes intensity maxima and minima, as you would expect, and that is superimposed onto the scattering effect. Now what you can see there here, in fact if I just use the cursor just to pinpoint this here, that is the first minima, and we can read off the angle, the diffraction angle at which the first minima occurs, and we can use that to work out the nuclear diameter. Now, as a task, I would like you to explain the shape of that graph. Obviously, we've just talked about it now, but you need to include those 4 keyword stroke phrases that are included in the word bank. So pause the video, have a go now at summarising that, please, and then press play. Okay, so we use this experiment to determine the size of the nucleus. By reading off the angle of the first minimum, the size of the nucleus can be calculated using the diffraction equation sine of theta min equals 1.22 lambda over d. Now I appreciate I've plucked that equation out of thin air and given no derivation for it. It should look quite similar to the equation that you've seen before, n lambda equals d sine theta, but of course the difference there is that we've got this value of 1.22 being used. Now I'm not going to prove that in this course why that is there, but it's to do with the fact that the diffraction is being caused by a 3-dimensional sample size, which means that essentially the diffraction is being caused by a circular aperture. That's something that we would look at more on the astrophysics option if you are studying that. So, another task for you, please. I want you to discuss why electron diffraction gives a more accurate value of nuclear radius than using the distance of closest approach of alpha particles. Pause the video and try to come up with at least 3 explained points for your answer. Press play once you've had a go at the task. So, why is it that electron diffraction gives a more accurate value for nuclear radius than using the distance of closest approach method? Let's look first of all at the flaws that come with distance of closest approach. First of all, the alpha particles have a mass that is the same order of magnitude as a nucleus. The result of that then is that the nucleus will actually recoil slightly when the alpha particle approaches it, because yes, the nucleus puts a force onto the alpha particle, but the alpha particle will also put a force onto the nucleus, which makes it recoil, and that is going to affect the results of the experiment. The distance of closest approach method also depends on the initial kinetic energy of the alpha particle. Remember that the more energy that the alpha particle has initially, the closer it will get to the nucleus, and so reduce the distance of closest approach. Let's not forget either that the closest approach does not actually equal the radius of the nucleus, but it does set an upper limit on what it can be. So you can have 4 points there for explaining the flaws that come with the alpha scattering experiment. You can then get another mark for pointing out that the de Broglie wavelength of high energy electrons is the same order of magnitude of the nuclear radius 10 to the minus 15. That means that we're going to get significant diffraction occurring, so that produces a nice large diffraction angle. You could also go on to say that that's an advantage because if you include a large diffraction angle, then that means that the percentage uncertainty in that measurement is going to be low. So, experiments to determine the radius of the nuclei then allowed scientists to produce an approximate empirical formula for the radius of a nucleus, which shows that the radius of the nucleus is dependent on the number of nucleons in it. A nucleon is essentially the collective term for protons and neutrons. That equation is given as R, which is the radius of the nucleus, equals R0, which is a constant equal to 1.2 times 10 to the minus 15, multiplied by A, which is the number of nucleons, to the power of a third. Now let's have a go at an example question which brings in some of the maths, an extra demand in the maths, more like A-level type of mathematics. If you haven't done already, you will of course need to watch the maths lessons that are for the A-level physics students about exponentials and logarithms to be able to access this content. So, a graph is plotted from experimental data that shows the mass number A and the nuclear radius R for a variety of different elements. The graph is plotted such that ln of R is on the y-axis and ln of A is on the x-axis. And then we have 3 questions. State the value of the gradient, state the significance of the y-intercept, and sketch the graph. So I'm going to just sketch the axes of the graph to begin with so that I know what I'm dealing with. I've got ln of R on the y-axis, ln of A on the x-axis. Now let's look at the equation, because the equation, the empirical equation that's given to us is written as R equals R0 A to the power of a third, but neither R nor A appear on that graph. We want the logarithms of them. So we need to rearrange this equation then to get logarithms in it. So we could take the natural logarithm of the left-hand side, which will give me ln of capital R, and then I can take the natural logarithm of the right-hand side as well, which will give me ln of R0 a to the power of a third. Now, unfortunately, on that graph, I haven't got ln of R0 a to the power of a third, it's just ln of a. So I'm going to need to apply the laws of logs that came in that first Maths for A-level physics lesson. So we know that we can split up that right-hand side to be ln of R0 plus ln of a to the power of a third, which is looking more like it. But I've still got that power of a third there, so I need to use another rule of logarithms to bring that a third down and put it in front of the ln, as so. Now that is going to be very handy because I've got ln of R and I've got ln of A. Now let's consider, we don't know at the moment that this graph is going to be a straight line, but let's assume that it's going to be. If it is a straight line, it of course obeys the equation of a straight line, which is y equals mx plus c. Now on the y-axis we've got ln of R, and on the x-axis we've got ln of A. Now comparing that then, you can see that m would have the equivalent of a third, which gives us the answer to the first question, meaning that the gradient is going to be equal to a third. It then says state the significance of the y-intercept. So the significance of the y-intercept, then you can see that the y-intercept is equal to ln of R0. That means if we read off what the y-intercept is, then we can of course work out a value of R0 by doing e to the power of whatever that y-intercept is. Now let's consider what the graph would look like. It's got to be a straight line because it's of the form y equals mx plus c, but it won't go through the origin. Please don't make that mistake. We get to the point where we're so used to drawing straight lines through the origin, we think it's part and parcel of the course. Of course, it's not here. We do have a y-intercept, and so we should include a y-intercept on our sketch. Okay, nuclear density then. Assuming that a nucleus is spherical, it of course has a volume that is equal to 4/3 pi times that radius of the nucleus cubed. Now we have an equation for the radius of a nucleus. We know the radius of a nucleus is r equals r0 a to the power of a third. So we can come up with an equation for the volume of a nucleus, which is 4/3 pi r0 cubed multiplied by a, where a of course is the nucleon number. That means that the volume of the nucleus must be proportional then to its mass. The reason for that is that the mass of a nucleus is equal to the nucleon number times by the atomic mass unit, AU. So we can see that the density of the nucleus, which is of course mass divided by volume, will be AU divided by 4/3 pi r0 cubed A, and then obviously with a bit of cancellation and bringing the 3 onto the top, we find that the density of the nucleus is 3u divided by 4 pi r0 cubed. We can conclude then that the density of the nucleus is independent of its mass and that the nucleons will always be the same distance apart from each other regardless of the mass of the nucleus. Right, so I'd like you to have a go at both sets of summary questions. The starting ones are grades B and C, and then it progresses on to the more challenging grade A questions. Question 1. For each of the nuclei shown, which is a helium, lithium, iron and uranium, I want you to calculate the number of protons, number of electrons, number of neutrons and the nuclear radius, but giving your answer of nuclear radius in units of femtometers. Pause the video, have a go at all of those questions and then press play to mark your work. So let's start off with 1A, which is helium. Helium, of course, has 2 protons in it. We can see that by the bottom number. It's going to have 2 electrons, because if for a neutral atom, the number of protons is always equal to the number of protons and electrons are always equal. Part C was the number of neutrons. Now bear in mind that top number, the mass number, is protons added to neutrons. So 6 take away 2 is equal to 4. And then it wanted us to work out the nuclear radii in units of femtometers. We use, of course, the equation R equals R0 a to the power of a third. Substituting the numbers in, our R0 is 1.2 times 10 to the minus 15. Timesing that by the number of nucleons, which is 6 to the power of a third, comes out as 2.18 times 10 to the minus 15 meters. However, the answer that we are required to give is in femtometers. Femto is times 10 to the minus 15, so the final answer is 2.18 FM. Very similar way of working here for lithium, exactly the same logic used here. Protons is equal to 3. The number of electrons is the same as the number of protons, and of course 9 take away 3 means that there are 6 neutrons. Same process for calculating the nuclear radius as well. R is equal to R naught a to the power of a third. R naught is 1.2 times 10 to the minus 15, times that by a to the power of a third, which is 9 to the power of a third, so that comes out as 2.5 times 10 to the minus 15 metres, and of course we get rid of that standard form to write it in femtometers as I have done for you there. Continuing on, this question really is just all about building fluency really, so we'll just quickly go over these. Protons will be 26, electrons 26, neutrons 30, and the value of the radius in femtometers is 4.59 femtometers. And then the uranium, by far the biggest nucleus, would have 92 protons, by far the biggest here, I should have said, 92 protons, 92 electrons, 143 neutrons, because we're doing 235 take 92, and then the radius will come out as 7.41 femtometers. Question number 2. A beam of high-energy electrons directed at a target are diffracted by the nuclei. Sketch a graph to show how the intensity of the electrons varies with the angle of diffraction. So this is a straight recall question that should come from your notes. Of course, it would have a shape like that. The intensity of the electrons is a maximum for 0 angle of diffraction. It then decreases to a first minimum, rises back up, and then drops down again. Question 3. In a visual model of the atom, the nucleus is represented by an apple of diameter 8 centimetres. Estimate the diameter of the atom in that model. So, we know of course that in reality the diameter of an atom is of order of magnitude 10 to the minus 10 metres. We also know that the diameter of the nucleus is of the order 10 to the minus 15 metres. Now, by doing a bit of quick division, we can see that the atom is then 10 to the power of 5 times bigger than the nucleus. Now, because the apple is representing the nucleus and it's of a diameter 8 centimetres, we're going to put 8 centimetres into metres and then times it by 10 to the power of 5. That gives us an answer of 8,000 metres or 8 kilometres. Question number 1 on the grade A. Determine the number of nucleons in a gold nucleus. A gold nucleus has a radius of 7.16 times 10 to the minus 15 metres. R0 has a value more specific in this question of 1.23 times 10 to the minus 15 metres. So, we want to work out the number of nucleons, so we're going to be using the equation R equals R0 a to the power of a third, but we now need to rearrange this equation to make A the subject. The starting point is obviously quite straightforward, we just divide by A0, but now we need to get A on its own. The most common mistake I see here is timesing by 3. Of course, we don't times by 3 because that's the power of a third is in the power, so we need instead to cube both sides of that equation. A to the power of a third cubed is equal to A, and R over R0 cubed is R cubed over R0 cubed. We then substitute the values in that were given in the question, so we do 7.16 times 10 to the minus 15 all cubed, divided by 1.23 times 10 to the minus 15 all cubed, which comes out as 197. Remember, of course, that it has to be a whole integer value. You can't have 197.2 nucleons because the number of nucleons has to be an integer. Question 2. A beam of monoenergetic electrons are diffracted by a thin metal sample in a vacuum. The number of electrons detected per second n at various angles theta were measured. The results were recorded in the table below. Now please note that of course we've not just recorded the number of electrons there, it's been recorded as the logarithm of the number of electrons. Now when you see log written there, do not confuse that for the natural logarithm. Log means log to the base 10 of n. Okay? It then says use these results to show that 50 times more electrons per second were detected at the central maximum than were detected at a diffraction angle of 75 degrees. So we need to start off by getting this table into just the actual numbers of electrons, and to do that we're going to use that way of writing logs that I've got on the board there. Logarithm of base a, n is equal to x, and that's how we solve an expression of n equals a to the power of x. So if we know that log of n, was to equal 2.3, we use that exact same logic then to say that n itself is 10 to the power of 2.3, and that of course comes out as 199.5. We then use the same logic to say that log to the base 10 of n equals 0.6 means that n is going to equal 10 to the power of 0.6, which on the calculator should come out as 3.98. Now, the whole point of this was to show that that is 50 times more, and so we do 199.5 divided by 3.8, which comes out as 50.1, and so hence we have shown that 50 times more electrons were detected at the central maximum than they were at 75 degrees. Question 3. Sketch a graph that has r cubed on the y-axis and a on the x-axis. R is the radius of a nucleus, a is the mass number of the nucleus, and then calculate the actual gradient of the graph, given that r0 is equal to 1.23 times 10 to the minus 15 metres. Let's start off by considering the equation then. We know that r is equal to r0 a to the power of a third, but we don't want to be putting r and a to the third on this graph. We need to be putting r cubed on it. So we cube both sides of this equation to give us r cubed equals r0 cubed a, and then we compare that to a line of y equals mx plus c. Now you can see in this case there is no plus c, so that makes life easier. When it comes to sketching the graph, it will just be a straight line through the origin. But now we need to calculate the gradient of the graph, and we can see that the gradient, m, is equal to r0 cubed. So the gradient will be 1.23 times 10 to the minus 15 cubed, which comes out as being equal to 1.86 times 10 to the minus 45 metres cubed. Please don't forget that because we're doing that r0 cubed, the unit also has to cube, so the gradient has that unit of metres cubed.